Welcome to day 3 of this workshop on high performance analog and mixed signal system design. Today we will be discussing, in this first session, we'll be discussing switched capacitor circuits. So a little bit of background why we look at these kinds of circuits. So if you look at CMOS technologies, we have very good transistor devices, especially if the transistors are used as switches. Okay, so the process technology allows construction of good quality capacitors as well, along with transistors, because the way the silicon layout is, the entire chip is constructed, if you see, it has basically transistors in silicon and then different layers of metal interconnects. So these metal interconnects processes are so well optimized that it becomes possible to make very good quality capacitors. Okay. However, it is difficult to get large resistors and inductors with good quality factor. Okay, inductors you can still make by uh, using loops of the same conductor, but since the area is very small, the inductance that you get and since it is so close to silicon, the parasitic capacitances of that inductance will be quite high, which means, put together, it means that the quality factor of inductors is very poor. It's also very difficult to make very large resistors. Okay, so even for circuits which require small values of resistors, setting time constants accurately is always challenging. Okay, so for example, if you say, okay, I need a resistance of 200 ohms, the process variations or the variations in the resistance value from chip to chip, from two resistors within the same chip, also is quite high, because the entire CMOS process is optimized to give you the best transistor performance. That's because the market is mostly dominated by digital circuits. So all the process technologies, at least most of them, are optimized very carefully for very good transistor performance and not for any other components. And in transistors also, the prime component that is optimized is the transistors on-off performance, basically transistor as a switch. So this creates problems in designing good analog circuits, which often require capacitors, resistors, sometimes also inductors, and so on. So we try to avoid inductors altogether to the best extent possible. And we will see how we can avoid the use of resistors by using capacitors and switches and make better types of circuits in CMOS. Okay, so switch capacitor approach is a way of designing circuits like filters and amplifiers, etc., which do not require resistors. So the basic idea is very simple. So what does a resistor do? It just controls the current flowing between two terminals based on its resistance value. Okay, so effectively what it means is that it regulates or determines the rate of flow of charge between two terminals of different potentials. Okay, so can we achieve a similar function using switches and capacitors? It turns out it's very easy. The rate of flow of charge between two terminals can be controlled by using switches and capacitors as shown. Okay, here phi 1 and phi 2 are non-overlapping clocks. When I say non-overlapping clocks, essentially what it means is that they don't have any period of time at which both phi 1 and phi 2 are high. Okay, so phi 2 will be something like, so there will be a small period of time when both phi 1 and phi 2 are off, and that is shown here. Both phi 1 and phi 2 won't be on simultaneously, which means that V1 will never be short to V2. So V1, V2 will never be connected directly, because phi 1 and phi 2 will never be on simultaneously. That is achieved by non-overlapping clocks. How to do that, we will see very soon. Okay, so how does this essentially work? When phi 1 is high, the capacitor C charges to voltage V1, and the charge across the capacitor can be written as Q1 is equal to C into V1. Next, what happens is phi 1, phi 2 are non-overlapping. So phi 1 turns off first, and then after a small period of time, phi 2 turns on. So the moment phi 2 turns on, the charge across the capacitor changes, because the capacitor is now charged to V2. So the total charge across the capacitor becomes Q2S, which is C times V2. So in first phase, the charge was C times V1. In the second phase, the charge becomes C times V2. So which means that effectively there is a charge transfer of Q1 minus Q2 into V2, right? So the change in the charge after this sequence is the charge that is drawn from V2. Basically, that charge drawn or dumped, depending on the absolute difference between V1 and V2. The total delta Q that goes into V2 is given by C into V2 minus V1. So because it was at Q1 initially, and the moment you close phi 2, the charge changes to Q2, the difference has to go to the voltage source V2. So this delta Q is C into V2 minus V1. So basically, delta Q charge is drawn from V2 in every clock cycle. If phi 1 and phi 2 are driven by non-overlapping clock, every clock cycle, this charge delta Q will be transferred from V1 to V2. Therefore, the rate of flow of charge can be determined as dq by dt, which is nothing but in every cycle, C into V2 minus V1 charge goes from V1 to V2, and divided by the time period is basically the clock frequency or the clock period t. So this can be written as Fc into V2 minus V1, where F is nothing but 1 over T. So effectively, this network appears like a resistance of 1 over Fc. Okay, of course, it's not a continuous time resistor, so the current comes in spikes, but the average of the current will be same as what is the current drawn from a resistor of value 1 by Fc. So if the switching frequency is much larger than the signal frequency, and if the output is band limited, then this is a good approximation for a resistance. Okay, so we have seen in yesterday's sessions how to make good switches in CMOS. Now what remains is how to generate non-overlapping clock. It's a very simple digital circuit to generate non-overlapping clock. So if I have a clock signal here, what happens is when you pass it through this digital circuit, you will basically get a non-overlapping clock. Maybe I'll just quickly work this out. If this is 0 and this is 1, what happens? 0 into whatever signal is here will be 0. This will be 1, and this will get a 1 after 2 inversions. Therefore, this is 1, and this is 0, and this 0 will come here. Okay, so this is the steady state of the circuit. When the clock goes from 0 to 1, what happens is this output doesn't change, right? Immediately. So this remains at the same state. Whereas when the clock goes from 0 to 1, this signal here goes to 0. Therefore, this signal goes to 1. And after some time, this signal goes to 1. So for the period of the delay of these inverters, so if this delay of this inverter is, let's say, 2 inverters is tau, then for the period of these 2 inverters, the upper phi 1 doesn't change. Okay, after that, what happens is after this becomes 1, then after some time, what will happen is this will become 0 and this will become 0. So there will be a delay of 2 inverters between the clock going from 0 to 1 here and the phi 1 going from 1 to 0, right? Oops. Okay, not phi 1 going from 0 to 1, right? So the clock going from 0 to 1 and phi 1 going from 0 to 1. Because of this inversion here, there will be a delay of roughly 2 inverters, right? And what about phi 2? If you notice phi 2 went from not 2 inverters, right? Sorry, 4 inverters. This will be a delay of 4 inverters because the signal has to go through, if I just trace it here, the signal has to go through these 2 inverters here, come here, make this as 1, and then flow through these 2 inverters. So there will be a delay of 4 inverters. Whereas if you see phi 2 becomes from 1 to 0 after a delay of 2 inverters. So what happens is every time the clock goes from every time there's a transition of the clock, phi 2 goes from basically rising edge of the clock. Phi 2 goes from 1 to 0 after delay of 2 inverters. Phi 1 goes from 0 to 1 after delay of 4 inverters. So there will be a period delay of 2 inverters between these two clocks, wherein both phi 1 and phi 2 are 0. Similar thing will happen on the falling edge. So basically this will give you a non-overlapping clock which has a non-overlapping period of 2 inverters. Okay, if you replace these 2 inverters and instead of 2, if you put 4 inverters, you will have 4 inverters delay. So basically you can control the duration of the non-overlapping period by controlling the delay in this path. Okay, so that's very easily done using only digital circuits, so that is not a problem. Okay, so let's look at a simple example. Let's say you want to make a integrator. Generally in an op-amp based integrator, what you have is you will have a resistor and a capacitor like this, and V out will be proportional to integral of V in dt. Now this R, if you want to replace it with a resistor made out of switch capacitor circuits, very simple. We'll just put the network that we just saw, 2 switches and 1 capacitor C, choose the frequency of the clock and the capacitance value to get the desired time constant. Basic circuit, it will work as an integrator, no problem, but there are some non-idealities which we will look at, which cause problems in the accuracy of this integration operation. What it is, basically it's the same things that we saw yesterday, charge injection, clock feed through, but how to address that we will see. Okay, one of the problems here is there is a parasitic capacitance from on this node. Let me say this node is X. So if you see from X to ground, there is a parasitic capacitance which is the drain to okay, if I say this is the drain of this transistor S1, the drain to ground, whether it is drain to source and then to ground, or whether it is from the substrate, drain to substrate and substrate to ground, whatever, the total drain capacitance to ground will appear here. One of the issues is this drain capacitance is non-linear, right? It's basically some kind of a diode MOSFET capacitance combination. So it is a non-linear capacitance. So what happens is whenever phi 1 turns off, there will be a charge injection onto this capacitor C, which will depend on the input value. So in addition to that, there is a non-linear capacitance on this node X, which means that for the same amount of charge dumped, the difference in voltage will be dependent on what is the absolute voltage at that node X. Okay, so this will result in some error in the non-linear error in the sampled value. Similarly, when phi 2 is turned on, that phi 2, one end of phi 2 will be at the common mode voltage of this or virtual ground, whatever you want to call it, of this op-amp, and therefore it will also inject some charge depending on whenever it turns on. Okay, so this will result in some non-linear error in the integration output, because this is something which is a charge injected which is non-linear. Okay, so this can be addressed again by just using a smart combination of switches which are clocked in a particular sequence. So this is basically addressed by using 4 switches, S1, S2, S3, S4. So what is done is in sampling phase, S1 and S3 are closed. So the equivalent network looks like V in to ground, which is the same as this network. When the sampling phase, when S1 closes, what happens is your equivalent circuit is V in to ground, right? So and the entire V in basically gets the capacitor C gets charged to V in. Only thing is here it is getting connected through 2 switches. That's all. Okay, and in the second phase or in the integrating phase, what happens is S1 and S3 open and S2 and S3, S2 and S4 get closed, in which case the circuit looks like this. So effectively it is the same as this. Even in this case, even in this simple network, in the integrating phase, what you have is the same network. Basically, S2 is closed, S1 is open. So the equivalent circuit looks like what is shown here. Okay, so the basic thing is that fundamentally nothing has changed in the sampling phase and in the integrating phase. The equivalent circuits are same. But what is this different arrangement of switches? So what is done here is during the sampling phase, S1 and S3 are on, S2, S4 are off. Nothing special there. That's what I just discussed. But when you're switching from sampling phase to integrating phase, what is done is first S3 is turned off. Okay, S3 turns off first. What happens is when S3 was on, both the terminals of S3, which is the drain and the source, were at ground. Okay, when I say ground, it's basically the AC ground of this op-amp. So basically, it will be VDD by 2 or the reference voltage, whatever is being used. But basically, a fixed potential. Okay, so therefore, when S3 turns off, the charge injected by S3 onto the capacitor C is fixed. It doesn't depend on the input voltage. So basically, it just produces an offset error. Okay, that also is minimized to some extent. We will see how. Okay, so S3 turns off first, injects a charge which is fixed amount, depends only on the clock voltage and ground, basically the difference between these two. After a short period of time, S1 is turned off. Now when S1 turns off, what happens is it will inject some charge. Its channel charge has to go somewhere. Where will it go? There is no path towards C to ground because there is no path to ground from here. Therefore, the charge through S1 cannot go to the capacitor C. So what happens to the charge through S1? Most of it goes through to the input side. A small fraction will also come to the parasitic capacitance on from this node to ground. Okay, but nothing goes into C. So no charge will go to the capacitor C simply because this S3 is off and there is no path to ground. Okay, so this charge has to go to most of it will go to Vi and some small fraction will come to the parasitic capacitance on this node here. Let me call this as node Y. Okay, after that what happens is S2 and S4 are turned on. The moment S2 turns on, what happens is whatever charge was injected onto this parasitic capacitance goes to ground. So the parasitic capacitance effect is no longer there in the network. Whatever charge was collected by the parasitic capacitance is discharged to ground. So the nonlinear capacitance effect is not going to be there. S4 turns on. The moment S4 turns on, S4, remember, it's a MOS turning on. So it has to collect some charges to establish its inversion layer. Okay. So where will that charge come from? It has to come from either from this capacitance C or from the integrating capacitance here, whatever is there here, CF. Okay. So some of it will come from this capacitance C and some of it will come from CF. Okay. Whatever is taken from C, in some sense, it compensates for the charge injected by S3. Okay. You remember when first S3 turned off, it injected a fixed amount of charge onto the capacitor. Now some of that fixed amount of charge will be taken out in order to establish an inversion layer in S4. Okay. So that reduces the offset to some extent, but even whatever residual offset is there, it is a fixed offset. It doesn't depend on the input voltage. Fixed offset, as we even discussed yesterday, is easy to handle. Any non-linearity becomes very difficult to calibrate and compensate, but fixed offsets are very easy to handle. You just have to either calibrate it or record it and compensate for it, subtract it later. Okay. So just by using 4 switches, we are able to ensure that there is no problem of charge injection on any of this during any of these turn-off transients. Okay, clock feed through will be there, but again, clock feed through is also something which is independent of the voltage or the input voltage. So again, that introduces a what you say fixed error. But what happens is in this case also, you see every node has a switch connected, which either turns on or turns off in every cycle. So basically, you'll have complementary injection of clock feed through, which will also compensate each other to some extent. Whatever residual offset is there is a fixed offset, and it's not input dependent, so it's easy to compensate. Okay, it's clear. So basically, this is a simple way of making a active integrator using R and C without actually using an R, but using switches and capacitors. Okay, any questions here? Simple circuit. I'm sure, perhaps you would have come across this earlier. We are just trying to analyze and understand it. Okay, now let's take the next example. Let us say you want to make a op-amp based inverting amplifier as shown. Okay, is it possible to design this amplifier without using resistors? One simple-minded way would be that you take each of these resistors R1 and RF and replace it with something of some kind of this kind of network which uses two switches and a resistance. But that is something which is I mean, simple-minded solution. You can do it at work, but there are more elegant ways of doing it. So if you recall, the gain of this amplifier is minus RF by R1, right? But it is not necessary that we introduce give the negative feedback with resistors. You can even give it with any kinds of impedance. So if I instead of RF, if I put any Z, I will get a gain of minus ZF by Z1. Okay, so in principle, if I just use two capacitors, I will get this gain as minus Z of CF divided by Z impedance of C1. So this will be minus C1 by CF. Okay, so will this work? Yes? No, it won't work actually. Because what you need for a op-amp is negative feedback to establish the operating point. In this case, because there is no DC path from output to input, this node potential is not defined, and therefore any small charge which comes and sits on this node will basically result in saturating the op-amp, either going to plus Vsat or minus Vsat because of the gain and the integration of the amp which is done by the op-amp. Okay, so the operating point of this input side will not be fixed because this is a high impedance node. So basically operating point is defined. This node V minus can take any value of voltage in this circuit. Okay, and that will result in the circuit not working properly. So if you have to define the operating point, one way to do it would be just simply put a very large feedback resistance. Okay, if you put a very large feedback resistance RF here in shunt with CF, what will happen is for DC signals, the input capacitor is an open circuit. So for DC, C1 and CF are open, and the equivalent circuit looks like simply with one resistance RF. Okay, so this is like a unity gain configuration, which means that this will be at VCM, right? This is a unity gain. What is that comment? KVL is not satisfied with feedback capacitor, right? I mean KVL at DC. KVL at DC. Basically, operating point is not defined. So if you put an RF in parallel with CF, we will be able to define the operating point, and this circuit will work. What will be the gain of this amplifier? Gain will be RF parallel to 1 over S times CF upon RF parallel to 1 over S times CF plus, sorry, right? So at the frequency of operation, if the impedance RF is much larger than the impedance of CF, if impedance of RF is much greater than impedance of CF at frequency of operation, then the gain will almost be equal to C1 divided by CF. Hey, this is wrong, right? This is 1 over S times C1. It should be ZF by Z1. Okay. Yes. Okay, so if you choose an RF which is sufficiently large at the frequency of, if the impedance of RF at the frequency of operation is much greater than the impedance of CF, then the gain will be almost equal to C1 by CF. However, note that this amplifier will work only for AC signals. It won't work for DC. So it doesn't solve all our problems. So if you have to amplify only AC signals, and if you can somehow put a large resistance, it will work. But this is again not practical. The whole argument of today's session was we cannot make large resistors in CMOS. So can we use some kind of switch capacitor network to do this? So yes, it's possible. Here's a very simple circuit to do that. So if you want to use only capacitors and switches, you can set up a network like this. So what happens is this network will have two phases. During the reset phase, what happens is phi 2 is closed. So let me just draw the equivalent circuits in both the phases. In one phase, the equivalent circuit will look like this. CF and C1. Okay. In the next phase, what will happen is CF will be short circuited. So, sorry, this is not right. In the first phase, CF is short circuited, right? Yeah. So what happens in this case? This node is at VCM, or the what to say, virtual ground of the op amp. Therefore, this is like equivalently like saying that the capacitor is charged to Vin minus VCM. Okay. In the second phase, what happens is that this capacitor is connected into the network, because phi 2 closes and phi 1 gets opened. So what will be the output voltage here? So in the first phase, Q across the capacitor is C into V1 minus VCM. Let me call this as Q1. In second phase, what happens is phi 1 is opened and then phi 2 is turned on. So basically, this will see a negative step off from V into VCM, right? So because of that, what happens is this Q, the charge Q on this capacitor goes from this value of C1 into Vn minus VCM to basically C into VCM. So delta Q of C1 into Vin gets discharged from this node to ground. Therefore, what happens is minus delta Q, what is there on this side of the plate, will have to go to this capacitor, and that minus Q will establish a will basically pull charge of plus delta Q from the output onto this side. Okay, and you can just work it out. Because the capacitance values are different, you will find that the V0 is basically C1 by CF times Vn. Okay, in every cycle, what happens is the input capacitance C1 is charged to Vn minus VCM, and then it is discharged to ground. The discharge of the capacitance to ground will require the other plate to also expel some charge, which has only one path to go. It has to go to CF, and that basically results in the output voltage changing. Okay, so this is how we can basically arrange the switches to make an amplifier, which now this amplifier will work also for DC. because what is happening is you are not using any relative frequency dependent impedances. In every cycle, you're charging the capacitance and discharging it. If your clock frequency is sufficiently high, you will be able to work with DC signals up to a certain frequency, depending on what kind of accuracy that you want. Okay, this is a simple way to make a inverting amplifier using only capacitors and switches. Okay, and of course, op amps. So you don't need resistances. Yeah, this is okay. So many things you can do, whatever, many places where we have used resistors earlier, we can do the same thing using capacitors. One of the circuits we discussed yesterday was fully differential amplifiers, in which we've had a problem of detecting common mode. Okay, so we needed a common mode feedback circuit with high dynamic range. So it is, and we had seen one of the simplest ways of designing common mode feedback circuits was using two resistors. But those resistances will affect the gain and so on. We had seen all those things yesterday. So we can construct this CMFB circuit using switched capacitors which give high dynamic range if we have switches which have good dynamic range. So that we already know how to make good switches which give you good dynamic range. So this is a simple circuit to detect the output common mode and generate the common mode feedback. So these five transistors, let me name them as MN1, MN2, MP1, MP2, and let's say MN3. So these five transistors are the simple differential amplifier that we have, fully differential amplifier, which is what we discussed yesterday. The new network here is only this common mode feedback. So what happens here is, during one of the phases, what happens is you close these two switches and open these two switches and close this switch. So essentially what happens in this phase is, if the two capacitors will be connected like this. So this will be at VCM ref. This will also be at VCM ref. And this node comes to the current reference transistor, right? So depending on this current I and the geometry of this will have some VGS. Let me call this as MN4. This will be at VGS 4. Okay. So basically this node is at VGS 4. Therefore, the potential difference across each of these capacitances is VCM ref minus VGS 4. Okay. So this is what the reset phase is. In the next phase, what you do is you close these two switches and connect the capacitance to the output and open the other three. So then what happens when you do that is the equivalent circuit becomes like this, right? Yeah. So now what is happening here? So the capacitance initially was charged to VCM ref minus VGS4, and now it is connected to the output. So because you have connected it to the output, what happens is whatever VCM output was there here, whatever was the VCM of the output, that average value will appear at this node as the detected VCM, right? Because one of them would have been VCM plus V, other one would have been VCM minus V. The moment you switch on these capacitors, they will give you the average value, which is the VCM detected. Okay. And what will be the voltage across the capacitance? Initially, it was VCM ref minus VGS4. Now it will be VCM of the output minus VGS4 minus VGS3. Okay, so whatever voltage that was there here is now connected to the tail transistor. Okay, not being minus plus, right? So when I'm going from here to here, this will be the equation for the voltage across the capacitor. Now, if you size these transistors, when nominally VGS4 is all equal to VGS3, this will get cancelled and you will get a output of VCM, which is equal to the VCM ref. Okay, let us see what happens when there is a small mismatch. Maybe I'll just wipe this. Okay, if VCM ref, if the output VCM was more than VCM ref, okay, then what will happen is that this basically this capacitor was charged to VCM ref, this node, and this node was at VGS 4, right? Before the switch. Now after switching, this goes to VCM of the output minus VGS of 3. Okay, nominally you size the transistor so that the current here and the current required in this branch is such that these two VGSs are almost equal. So VGS4 can be nominally made close to equal to VGS3. But if VCM ref is, let's say VCM of the output is more than the VCM ref, then what will happen is once you switch back, this voltage will become slightly higher. If this voltage goes slightly higher, it will draw more current, and in the next cycle, the output common mode will fall. On the other hand, if the output common mode was actually less, then what will happen is every clock cycle, the subsequent gate voltage on this transistor will increase slightly in order to make your VCM equal to VCM ref. Okay, in this way, that a small negative feedback is established in order to make sure that the output common mode is where it should be, and we are only using switches and capacitors, no resistors in the circuit. Okay, in this way, we can just set up a common mode feedback in order to bias a fully differential amplifier. Okay, any questions here? Okay, let's move on to other uses of switch capacitor circuits. Switch capacitor circuits will, I mean, once you understand how to use them, you can use them smartly for doing various things. We can even use them to improve the matching in a current mirror. How will you do that? Generally, what is done in the current mirror is what is shown here. Very popular circuit. Everybody understands this. What happens here is, if these two transistors are matched, this current I will generate a VGS here, and then I out will be by 2 into VGS minus VTH, the whole square. Okay. If your transistors have high output impedance, then this 1 plus lambda VDS can be ignored. And if both these transistors have the same mobility and the same same threshold voltage, then both these currents IN will be and IOut will be equal. So this will be equal to IN if both the transistors are well matched. But what to do? What can you do if the matching is not that great? Okay, as you might be knowing that as technology scales, transistors are becoming smaller and smaller. Matching performance basically gets degraded as you make the transistors smaller and smaller. So can we improve the matching by playing some tricks? So one of the ways of doing it is, if I use the same transistor for generating VGS as well as for generating the output current, then I will not require two transistors which are matched. Okay, basically what we are trying to say is, we use only one transistor. So by reusing the same transistor to generate the reference VGS and as the current source transistor in different cycles, we can get very good matching. Okay, so what is done here is, you use an arrangement of switches to use the transistor to generate the reference with respect to IREF in one cycle and generate the Vout in the other. Okay, I have expanded this in the next slide so to make it clear. So when this clock is high, When phi is high, the equivalent circuit looks something like this. So Iref, the transistor is gate and source are connected together by this switch here. So this gate and source are connected together. There is a capacitance here which charges to VGS. Right. So this Iref now flows through this current simple reference circuit, what you say, diode connected transistor, to generate a reference VGS. In the next cycle, what is done is phi 1 is turned off, and after a short delay, phi bar goes high. Once that happens, is the gate to source connection is open, input side is disconnected, and the output side is connected. So what happens is this transistor flows a current which is proportional to VGS minus VTH, the whole square. Okay. Since it's the same transistor, that VT is same transistor, so mobility is same. So the matching performance is much better, right? Only thing is this will give you a pulsed output. You won't get a constant output current. You will get a pulsed output in which in half the cycle the current is 0. In the other half cycle you get a current of, which is an exact mirror of Iref. Okay, that's a very small problem. By using two complementary sets of such circuits, you can now generate a continuous current. Okay, if you want continuous mirroring of I into I out, all that you can need to do is make two copies of this. In one cycle, one transistor will be generating the reference, other one will be generating I out. In the other cycle, this one will be generating the reference and this one will be providing the I out. Okay, so by using two transistors, basically two sets of this kind of circuits, you can achieve constant continuous operation by using alternate by switching between two sources continuously. Okay, so this gives you continuous mirroring of Iref to I out with very good matching performance. Okay, simple circuit. There's nothing very complicated here. Just a smart way of using switches and transistors. Okay, any questions still here? Otherwise, I would like to move to a slightly different topic, which will require some discussion. We have discussed very simple circuits today here till now. So basically, first thing is understanding that resistors are difficult to make in CMOS processes. We saw how to make resistors using switches and capacitors, and how to generate non-overlapping clock for this, and what are the problems associated with, for example, making a simple switch capacitor integrator, how to address it using arrangement of switches, how to make inverting amplifiers using switched capacitor circuits, how to generate common mode feedback.
Hello, sir.
One thing is how to generate mirrors. Yes.
For switching type of integrator, how to select the value of capacitance C?
Switching type integrator. This one.
Yes, sir. How to select the value of?
This is very easy. So, for example, what is the integration here? V naught will be minus 1 upon RC integral of V in dt, right? So if you recall your basic integrated design, generally what we do is we choose the range of integration first, and then your where did this go? Sorry. You choose the range of integration frequencies. Okay, and then you will get a value of RFC. So in this case, the R is simply given by 1 over F times C. Okay, so by using the suitable value of R, you first calculate what should be R for that particular range of frequencies of integration, and then just use a C depending on what frequency of clock you have in the system. 1 over F times C should be equal to R. That is all that is there for the design of the integrating capacitor C. So CF is of course the same way as what you do in the normal integrator. So basically, to answer your question, it depends on the range of integration. You look one thing is you just design it in the conventional way and then just replace R with 1 over F times C. That's all.
Okay, sir.
Okay, any other questions? Otherwise, we will move to now this. If you look at our switch capacitor circuit discussion, we started with a statement that in CMOS processes, we get very good transistors as switches. Okay, so it's difficult to make resistors and inductors, and we have seen how to make resistors and inductors using switches and capacitors. And the argument was that okay, we get very good switches in CMOS, we get very good capacitors, therefore we can make resistors using switches and capacitors. And then we saw how to make simple circuits like amplifiers, integrators using, by which avoid use of resistors. But the problem is there is still an op amp here, right? There is still an amplifier there. So as technologies have been scaling, you might have been hearing about this also, that analog performance keeps getting degraded, digital performance keeps getting improved, which means that again switching performance of devices is very good, analog performance is not that good. So what we have done by using switch capacitor circuits is we have eliminated the need for all the resistors in the circuit and replaced them with switches and capacitors. So switch capacitor circuits eliminate need for resistors in the circuits. Okay, but still there is an op amp, there is still amplifiers are still there, and we know that as technology scale, amplifier performance is not that good. Linear analog performance of transistors is not that great. So the question is, can we avoid the use of amplifiers also in some way and replace it with some circuits which work well in scale technologies? So to understand that, first we need to understand what does the op amp do in the circuit. Okay, what does any op amp do? So let me take the example of, for the ease of analysis, what I will do is, in this case, I'll take the example of this particular circuit, in which, or maybe let me take this circuit, okay, where you have C1, CF, and RF. What does the circuit do? Basically, what the op amp does is it integrates the difference between Vi plus and Vi minus, right? What does the op amp do? It basically drives the output node by integrating the difference between Vi plus and Vi minus. And because it is connected in feedback, it integrates till Vi plus minus Vi minus, the difference becomes 0. So till Vi minus becomes equal to Vi plus. Okay, this is what we call virtual short and all those things, virtual ground, virtual short, whatever you call it. Okay, basically what happens is that the output voltage increases, or basically output voltage changes until Vi plus becomes equal to Vi minus, at which point the circuit reaches a stable state and it stops there. Okay, so to put it in another way, what happens is op amp drives the output till Vi plus becomes equal to Vi minus, or so that it drives the output in such a way that Vi plus becomes equal to Vi minus. Now, can we avoid this op amp and still get the same function of Vi plus becoming equal to Vi minus? It turns out that it can be done by using a comparator instead of a op amp. Okay, so instead of using an op amp which amplifies the difference of Vi plus and Vi minus and generates and charges the output, if I can somehow use a comparator, so the suggestion is that instead of using a op amp, I will use a comparator. Of course, comparator's output is digital, right? So that is not good enough. So what I'll do is I'll take the comparator output and connect it to a current source and a current source and a switch. So basically what this does is in this case, what happens to V out? If for any small difference of V in, what happens is V out charges exponentially to charge the output to the final value V naught, which will make the input difference 0. In this case, what happens is whenever Vi plus is greater than Vi minus, then what happens is this switch turns on and the output charges with a constant current source. So basically what happens is the output charges with a constant current source. And once the output reaches the final value V naught, the comparator output value changes from 1 to 0 and the switch is disconnected and the output basically remains charged at V naught, right? So basically what we are trying to do is, instead of driving the output in such a way that Vi plus becomes equal to Vi minus, we will use a comparator and check the sign of Vi plus and Vi minus and either charge the output upwards or downwards until it becomes equal to Vi plus becomes equal to Vi minus, detect that and then disconnect the circuit and stay where you are. Okay, so basically we avoid the use of op amps and use only switches and comparators to do the operation of integration. Okay, so why is this better? This is better because it's easy to make comparators in CMOS. Basically, as technology scales, it's easy to make comparators because comparators only have to discriminate between the sign of the input. Linearity is not important. As technology scales, linearity performance degrades. If you can only determine the sign, if you can only make a very good comparator, even if it is not, I mean, comparators don't need to be very linear. As long as the offset is minimized, it is offset is small, it should be okay. And offset, of course, can always be calibrated. Second thing is this current source. It's just a, what you say, simple current source. It doesn't depend on what is the value of it. It doesn't need to be very, even if it is, let's say, even if it is having a finite output impedance, the current, it doesn't give a very constant current. It changes to some extent. It doesn't matter. All that you are doing is you are just waiting for the output to charge to the required value, and once you reach that required value, you detect it and then disconnect your circuit. So basically what we are doing is we are detecting the virtual short being condition being reached rather than forcing it and driving it to that condition. When you use an op amp, the op amp drives the output in order to make Vi plus equal to Vi minus. When we use a comparator, what happens is instead of driving the output to make Vi plus equal to Vi minus, we drive the output at a constant current and use the comparator to detect when Vi plus becomes equal to Vi minus and then stop charging at that point. Okay, I'll just draw the circuit again here, maybe in a little more, or maybe what I'll do is I'll draw both these circuits together so that our point becomes clear. Okay, in this case, what did the op amp do? In one cycle, of course, the input was charged to Vin minus VCM. In the other cycle, the equivalent circuit looked something like this. Right? So in the other cycle, what happened was there was a charge of delta Q which was injected onto this node that produced a voltage difference on this node, and the op-amp would have driven this capacitor until these two nodes became, the difference between these two nodes became almost equal to 0, which is when the desired output voltage would have been minus C1 times CF into Vn. This is what the op-amp based switch capacitor circuit had done. Now what we are going to do here is we are going to try to make this using switch capacitors, using comparators and switches. So we have a comparator here. And a switch. And the feedback capacitor C1 CF is connected here, and you have a capacitor C1 which is here. So now what happens here? The moment you changed the configuration from sampling to integration, what happened is this would have gotten a charge of minus delta Q. Okay, in this case, what is done is, for, okay, I should probably specify that before every cycle, when you are sampling phase, the output is also discharged to ground. Okay, so that forces the output always to start from 0, or in fact, I should say minus, okay, 0. Comparator turns on, irrespective of what is the previous cycle, since it is always shorted to ground. Every time you connect the capacitor to this input, what happens is that the output of this comparator becomes 1, and this current source gets connected to the output capacitor, and the output starts getting charged up. As the output starts charging upwards, at some point what will happen is this voltage will also start ramping up, right? By the ratio of C1 and, oops, why is this changing? By the ratio of C1 and CF, by that impedance ratio, this output is seeing a ramp here. So this also will start charging upwards. At some point, what happens is V minus will become greater than V plus. At that instant, what happens is that the switch turns off. And once the switch turns off, the output will stop charging and will hold that value wherever it stopped. Notice that what time did it stop? That the output capacitor stopped charging just the moment when Vi plus became equal to Vi minus. So output stops charging when Vi plus becomes equal to Vi minus. Right? The moment Vi plus becomes equal to Vi minus, the output stops charging. What does this mean? It means that the steady state of the circuit, when the output has stopped and the charging and the final value has reached, Vi plus is equal to Vi minus. And if Vi plus is equal to Vi minus, then the final value of this circuit to the right and the final value of this circuit to the left are same, which means that V0 will be equal to C1 by CF into Vn, right? Because that is the point when that is what was happening here also, right? Basically, what was the op-amp doing? It was driving this to 0. By driving that to 0, effectively what has happened is, in order to drive that to 0, it needed to maintain a potential difference between V0 and Vn, and that potential difference turns out to be C1 by CF times Vn. So the same thing is happening in the second circuit also. So basically, by using switches and comparators, we are able to generate the same function that the op-amp was doing. Now the advantage is you don't need linearity in any of these circuits. Okay, comparators are non-linear circuits. You don't care because you can make very good comparators in scaled CMOS processes. Making very good op-amps on the other end is very difficult.
Hello, sir.
Yes.
Sir, there is one doubt. Here we are using comparator. So is it op-amp as a comparator or internal circuitry will be different?
That's a very good question. I think what you're trying to say is whether it's a clock comparator or a simple op-amp as a comparator. This is op-amp as a comparator.
Yes.
Okay, so basically what this circuit is, basically it's just a chain of amplifier. See, op-amp, you have to be careful because you're going to use it in negative feedback as a linear circuit. In a comparator, you're not worried about linearity, you're not worried about stability as such, because you want the output to saturate. Okay, so
Okay.
you can just use 3-4 amplifiers in a chain and make sure that the output reaches to the highest possible value. So the linearity of this amplifier is not very important. So
Okay.
it's
So
just
that is the
optimized
difference only.
comparator.
Okay. Means construction wise, there won't be any difference. It is also op-amp, but
Well,
we have
no,
to, we
construction
can,
wise, there will be a difference because the thing is that you're not going to use it as an op amp, right? So you don't have to worry about phase margin, those stability, and those kinds of things.
yes.
So you can just
Even
use.
gain,
Uh-huh.
even gain, na? Gain also?
Gain should be high. Comparators gain should be high,
Okay.
but you don't need linear gain. See, high gain
Gain.
is difficult in scaled CMOS only when you're looking for high gain with high linear range. If you're okay with non-linearity, high gain is very easy. So, for example, you can use a weak positive feedback in this amplifier to get very high gain. It will be non-linear, but since your output is just going to be 1 or 0, it doesn't matter. Okay, for example,
Yes.
one simple thing you can do in this is you can use one differential amplifier, or maybe even 2 in a chain. I'm showing it with resistance, but you can use any transistor based circuit also. And then you can just use the
Yes.
inverter to take it to rail to rail. Even this will work. For example, this kind of using an inverter to take a small differential voltage to rail signals as an amplifier will never work in an op amp, right? Because it's very difficult to control the operating point and all. But here you don't mind about all those things. So the type of comparator that you need here can be easily made with even in digital CMOS processes.
Okay, sir. Thank you, sir.
So since you asked that question, I will just show it. One simple way to do it would be okay. So this is a simple differential amplifier which has a differential input and differential output. You can use 2 or 3 of these stages. Since you're not using it in linear feedback, you don't have to worry about stability. And then after using 2 to 3 of such stages, what you can do is you can use a okay. So this is basically will convert differential amplifier to differential input to single end output, and then use an inverter to, or even maybe chain of 2 inverters to take it to rail signal. Okay, so by using a cascade of such amplifiers, you can easily convert a small differential input to a proper digital decision, which is either +1 or -1. All that is important now here is that this op amp should have very low. This amplifier chain should have very low offset. So you don't want offset to affect the transfer of basically the decision from +1 to -1. Strictly speaking, it doesn't matter much. Just the way offset affects the final value of this op amp. Even in this case, when you have an offset in the op amp, it will produce a offset in the output. The same thing will happen here. Instead of settling to V0 minus C1 by CF times V in, it will settle to minus C1 by CF times V in minus C1 by CF times some small V offset. So it is going to produce the same kind of error that the op amp circuit would have done. It's not like you are getting a whole new big problem. So, and the same techniques which are used to compensate for offset of op amp can be used to compensate offset of comparator also. Okay. So, and as I said earlier also, offset errors are generally not very troublesome. they are easy to correct for, because it's just a fixed value, fixed DC shift, unlike non-linearity, which is very difficult to compensate for once it comes into the system. Okay. So this is how we can make a switch capacitor amplifier without using any amplifiers, by using only switches, comparators, and capacitors. Okay. So one of the concerns with this is that what will be the speed of this comparator? Okay, let me just what is the use of inverter with DFA? What is DFA?
So it
Mr.
is
Deepak,
differential amplifier. DFA is differential amplifier.
okay, differential amplifier. What is the use of inverter with DFA? Here, what I have drawn here, this is a comparator. This entire circuit together is a comparator. So the output will be +1 if the input difference is positive. It will be -1 if the input difference is negative. -1 means 0, right? So it's not a differential amplifier; it's a comparator. Basically, it's a chain of differential amplifiers which takes the input, small differential input, to a sufficiently large value, and then two inverters will take it to proper decision of logic 0 or logic 1. Okay, I hope that answers the question. Now, so the point I was making was, what will be the speed of this circuit? So if you want to make the speed of the circuit high, what you will do is, basically, when I say speed of the circuit, what does the circuit do? In every cycle, the output starts from 0 and starts charging up. Once it charges to a sufficient value that the virtual short condition has been reached, it will settle there and stop, right? So now let us look at this entire mechanism a little more carefully. What exactly happens when the output starts charging up? As the output starts charging up, the comparator will detect that the virtual short condition has been reached, and it will turn the output off. But this will have a delay of the comparator. So what will actually happen is, when the virtual short condition might have been reached at time t equal to t0, but actual output of the comparator will basically, instead of stopping here, it will charge a little further and stop here, right? So there will be a small error due to delay of comparator. Okay. So now if you want to make this circuit fast, then what you will do is you will use a large value of current here. If you use a large value of current, the error in the output will also be correspondingly larger, right? So this is a problem, because if you use small current, then error will be very small, but the circuit will take a lot of time to charge to the final value. If you use a large current, circuit will settle fast, but it will settle with a large error. So can we work around this? It turns out that you can do it with just by what you can do is you can use a large current to allow this additional overshoot, and then use another comparator, or use the same comparator with to basically discharge another this output with a smaller value of current. So what I'm trying to say is, I'll shift this here. If I use a comparator like this, so I have a large current I large, which is going to drive the output capacitor, and I have a smaller discharge current, which is, so here there's a switch, right? So, and I have a comparator. I'm not going to draw the entire circuit for keeping it simple. So what happens is when Vi minus is less than Vi plus, this output is 1 and this switch is turned on. Right? So this is when Vi minus is less than Vi plus. What happens to the output at that time? The output at that time will basically start charging up. Okay, this is my desired output value. Once the output of the comparator changes, basically once Vi plus minus becomes more than Vi plus, the comparator detects it and this output will go from 1 to 0, right? But because of the delay of the comparator, the actual output would have overshot and it would have settled somewhere to this point. What we will do is we will detect that condition and control this switch. Once the output crosses, basically once the comparator output goes from 1 to 0, that output is then inverted to turn on the I small. So what this I small is a small current which will discharge the output with a smaller value of currents. So this I small will now start discharging the output with a much smaller slope. Okay. Now what happens is once what will happen is now Vi minus will start reducing. Once Vi minus becomes slightly greater than Vi plus, this comparator will again turn on and it will disconnect the Vi minus also. Okay, now it's not a simple just on-off kind of condition. You need a small logic circuit which detects this sequence. So basically what you need to detect is you need to detect the sequence of the comparator output going from. So now it's just a simple FSM design, right? Initially comparator output will be 1. It will go to 0. After it goes to 0, I small will get turned on, and then as I small starts discharging the current, after some time comparator output will become 1 again. So you need, and initially when the entire circuit was reset, of course the comparator output would have been 0. So you need a small digital circuit which detects the first 0 to 1 transition. Once it detects the first 0 to 1 transition, it should turn on this I large, allow the output to charge up, wait for the next 1 to 0 transition. Once the second 1 to 0 transition happens, turn on this small current I small to discharge the output. And then when that I small discharges the output such a way that Vi minus becomes slightly less than Vi plus, after that time, you will have to detect the comparator output again going from 0 to 1. And when that happens, you close both switches, both these switches S1 and S2. Okay, and then the output will stay where it is. Since the second current I small this discharge current is much smaller value, the delay of the comparator in turning off the current source will result in a very small offset voltage. So the error will be much smaller. So in this way, what is happening is you're using a very large current to go from 0 to approximately close to the output value with a significant amount of error. Then the small current comes in to gradually reduce from that output value to a more accurate version of the output. Overall, the speed is much higher, error is much smaller, and all that you are doing is you're just using some small variations of digital circuits here only. Okay, any digital circuit is not a problem because as technology scales, our digital circuits become very much better than analog circuits. So any small complexity in terms of digital circuit is not going to hurt much. So all that we need is a small FSM to detect the sequence. Very easy to do. And a comparator, again, since you are just discriminating the sign, very easy to construct. And all that you have left is currents and capacitors and switches. Linearity of any of these components is not important because you are not dependent on any amplifying action as such. Okay, but still you're getting the amplification of Vin to V0 with a amplification factor of C1 by Cf. Okay, any questions here? So it's a very simple circuit once you understand it, but I think it's a very smart idea, which of using comparators rather than op amps. Okay, the only difference. So you look at the key differences here. What you are doing is in op amp, you are forcing the virtual ground. In comparator, you are detecting the virtual ground condition being reached. It's always more power efficient to detect a condition rather than force a condition. So it turns out that when you implement a circuit with comparators and switches like this, the overall power of the circuit will be much smaller than what you have for the op amps. And that makes sense also, right? Because when you try to make an op amp with high linear range, you will end up burning a lot of power to increase the linearity range. But if you are using comparators where linearity doesn't matter, you can do it with much lower power. Okay, so the key point is identifying what the op amp does. It integrates the output to drive the output in such a way that the virtual ground condition is met. In comparator based design, what you're doing is you're allowing the output to charge at a constant rate and waiting for the virtual ground condition to be reached, detect it, and then just turn off at that point. Okay, and a small modification to improve the speed is using a large current, a small current, and a small digital logic. So these kind of games you can start playing to get to the desired specification of speed and accuracy without using any analog circuits as such. So this is a very nice idea wherein you have an analog amplifier with not even one single analog component. Okay, just a fixed current source, comparator, and a few switches and capacitors. Yeah, any questions here?
Hello, sir.
Yes.
Sir, that means the inverters with DFA, so that is not required. No? Inverter is not required. We need a circuit, digital circuit, to detect this sequence 0 to 1 and 1 to 0.
No. The comparator is still the comparator is still there, no?
No, not a comparator. Inverters. You just drawn those two inverters.
This one.
Yes, this inverter.
Yeah, this is. I mean, this I drew just for illustration. This is not.
So this is nothing but a digital circuit. This will be a digital circuit, which will.
So basically, what is there here is there is a small digital circuit between the comparator and
yes. Okay.
Switches. So this is a simple digital FSM.
Yes, understood.
Which detects the sequence.
Which will detect that sequence. Yes.
Yeah, very easy to design. I mean, in fact, something which second year students do in our courses, right?
Yes. Actually, that you just have to write that code, RTL code, and
yes, very simple.
That is very easy, actually. Yes, sir. Okay, understood, sir. Thank you, sir.
Yeah. So I have. So again, whatever we have discussed today is there in this stand, and the switch capacitor circuits part is there in all of these textbooks. One is Bezaz Razavi and Gray Mayer's textbook on analog integrated circuits, or Jacob Baker's circuit on circuit design and layout. The comparator-based switch capacitor circuits is something which is somewhat more recent, and it's a very nice and easy to read paper, though it's a journal paper. But it's very easy to read and understand. You can just download it and read it. Very well written and simple circuits and simple idea, but very effective, as you can see.
Hello, sir.
Yes.
In the case of sigma delta ADC,
yes,
there is a chain of integrator followed by the comparator.
Yes.
So with this concept, is it possible we can replace integrator also with comparator? So there are two comparator in.
It should be possible. Yes.
Yeah.
So you can. I mean, not sure if everybody is familiar with delta sigma, but yeah, it should be possible to replace that integrator with this kind of with a switch capacitor based integrator. And I think it is also done many places, but I'm not sure whether they do it with comparators. I have not seen.
Okay.
Okay. Any other questions? If not, we will stop here. We'll take a break for about 15-20 minutes and return at 11:15 for our next session on comparator design. Okay, there we'll be discussing clock comparators, not these kinds of comparators. Not this one. We'll be looking at clocked comparators.
Okay, sir. Thank you, sir.
Okay, so let us stop here. We will take a break and we'll return at 11:50.